This is the most beautiful equation in mathematics. And in this video, we are going to prove this beautiful equation in maths from the scratch. Yeah, from the scratch, I mean. Okay, so let us begin. But before we begin, let me introduce you to these functions. So, first of all, this is digamma function. So, digamma function is just the derivative of logarithm of gamma function. But then what is gamma function? Yeah. What is gamma function? Gamma function is factorial of x minus 1. And what is factorial? You probably know that if you have come to watch this video. And now what is Euler-Mascheroni constant? This is limit n tends to infinity hn minus ln of n. Now what is this hn? Hn is the discrete sum from of the reciprocals 1 by 1 plus 1 by 2 plus 1 by 3 up to 1 by n. So these are the definitions of those functions we are reusing, and this can be simplified as derivative of gamma function by gamma function from the chain rule of differentiation. So this is digamma function, this is gamma function, this is Euler-Mascheroni constant. Yeah, it's a surprising fact that this in fact converges. The difference of the harmonic number, nth harmonic number, and ln of n does converge, and it converges to this constant gamma, which is Euler-Mascheroni constant, which is 0.57 something, and this is nth harmonic number, which is sum of reciprocals from 1 to n. Now after we know this, so how do we begin proving this statement? First of all, we need to get our steps will be, first of all, we need to we will try to get an integral representation for gamma function. After we have that, we will try to get a product representation for gamma function. First of all, we have integral representation and then product representation, and from that we will get infinite sum representation for digamma function, and after that we can derive this expression. So it might be a long journey, but I make sure that it will be an interesting one. So first of all, we will try to get an integral representation. So for this one, it was done for us by Euler, and it's really so well known that I don't think it needs to be done, and it's somewhat tedious as well. It's just kind of surprisingly known or patent trial, something like that. So basically, first of all, gamma function, which is x minus x1 factorial, it is given by this integral from 0 to infinity e to the power minus t to the power x minus 1 dt. So if you want to check if this is really x minus 1 factorial, you can just do integration by parts. So if this is I of x minus 1, if you do integration by parts, you will get t to the power x minus 1 and then e to the power minus t by minus 1 going from 0 to infinity minus integral from 0 to infinity, and then x minus 1 t to the power x minus 2 and e to the power minus t by minus 1 dt. And now at infinity, this e to the power minus t will just dominate the entire expression and goes to 0, and at 0 we have this as 1 and this as 0, so goes to 0, and this minus multiplies with minus to give plus. So I of x minus 1 is just plus x minus 1, this comes out, an integral from 0 to infinity t to the power x minus 2 times e to the power minus t dt. It's almost same as the original except that we have x minus 2 in place of x minus 1. So I can say it I of x minus 1 equals to x minus 1 times I of x minus 2. It's a kind of recurring function. We can see that now it goes on in the same pattern until we have x minus 1, x minus 2. So when we have 1 over here, we have 1 less than that, so I of 0. I of 0, we have t to the power 0, so that is integral from 0 to infinity of e to the power minus t dt. And this is e to the power minus 2 by minus 1. At infinity it's 0, at 0 it's minus 1, so that's 1. So I of 0 is just 1, and then we get x minus 1 factorial. Yeah, now we have got this expression now. Yeah, this was just 1. And now after this expression, we are using this expression to find its product representation. This is known as Euler representation. Now we are going to find Gaussian product representation. Now for that we have gamma of x as integral from 0 to infinity e to the power minus t to the power x minus 1 dt. Now we can expand this e to the power minus t to get integral from 0 to infinity, not expand but write in the other form. So t by x, t by n, let's say t by n to the power n, where n goes to infinity, and then limit n goes to infinity, and t to the power x minus 1, x minus 1 dt. Now limit n goes to infinity, so we can take it out and also change the limits of integral from 0 to n, and 1 minus t by n to the power n, since these are in the same order, and dt. Now we can integrate it using integration by parts, and so we get limit n tends to infinity. This is 1 minus t by n to the power n. Integral will be t to the power x by x from 0 to n minus integral from 0 to n. This is n times 1 minus t by n to the power n minus 1 times 1 minus 1 by n, and its integral will be t to the power x by x dt. So this is gamma of x, okay, gamma of x. So this will be at n, this will go to 0, at 0 this will go to 0, so it's 0 for both the values, and here minus will come out here to make it plus, and we also have n by nx. So that's n by nx, integral from 0 to n, and also the n is going to infinity, and over here we have 1 minus t by n to the power n minus 1, and t to the power x, to the power x dx. Now it's kind of same to the previous one, just that n is replaced by n minus 1 and x minus 1 by x. So when we had n over here, we got n over here, and this n over here, and x over here. So we can just predict what we will have now for the next integration by parts. We can just predict the next session of integration by parts. N by nx, we will have 1 n minus 1 in the top, and this n in the denominator, and this gives us x plus 1 now. And in the next integration by parts we will have okay, so we will here, let's write down for now 1 minus t by n to the power n minus 2, and t to the power x plus 1 dx. Now if you continue this infinitely, we get gamma of x as limit n tends to infinity, n times n minus 1 times till this one goes to 0. So at that time we will have 1 over here. 1 is just n, Let's numerator. So up to 1. Denominator we will have nx and then n times x plus 1. Yeah. And when it goes to 1, so this is n minus n minus 1. So we will have n times x plus n minus 1. Yeah. X times 1 minus 1. So you can, I think you can see this. Yeah, I guess. Because over, because over here, when we had 1, we have here 1. So this is just n minus n minus 1. So we get n minus 1 over here. Yeah. That's simple. And now after this, we have 0 to n. For 1, this should be 0. So this just vanishes. And this will be these and these numbers are same. So we will have t to the power x plus n minus 1. And then this is this dx? Huh? This was dt. How did it change to dx? How? This was dt. This was dt. How did it change immediately? So dt. Now after this we have gamma of x equals to, I'm really sorry for these noises, limit n tends to infinity n factorial by n to the power n, and then this is x plus 1 up to x. Okay, so x plus, this is not in power, right? This is just product. This is just product. Yeah. And x plus n minus 1. And this integral gives us t to the power x plus n by x plus n. And we evaluate from 0 to n. So if we evaluate this, we get n to the power x plus 1 by x plus n minus 0. So we have gamma of x as limit n tends to infinity n factorial by n to the power n times n to the power x plus n by x plus 1 up to x plus n. Yeah. And now we can just cancel these out, and we get this as limit n tends to infinity n factorial n to the power x by x plus 1 up to x plus n. In the other form of infinite product, we can write it as limit n tends to infinity n to the power x by x, infinite product from k equals to 1 to n, that is infinity. And this n factorial will be represented by k, infinite product, and this one by x plus k. And this is also known as Gauss representation for gamma function, like we had Euler representation earlier. This is Gauss representation for gamma function. Now we have further to do. Now we are going towards Fourier stress representation, which is just 1 by gamma of x representation, where these infinite numbers, this n, will be removed, and it will be made a lot easier for calculation. Okay, so we have limit n tends to infinity x by n to the power x, and from k equals to 1 to n, k equals 1 to n, and this will be 1 plus x by k. Now we can just bring it to numerator, and since we want to remove these infinite terms like n, we will have an idea now. So now we can take it to e form. So e to the power x ln of n can be made, and in the numerator e to the power minus x ln of n. Now if you just add plus x as n, we can take x common, and as n minus ln n, where n goes to infinity, is just Euler-Maslow constant. So that removes n completely. And if we just add it, we need to subtract it as well, e to the power minus x as n. and infinite product from k equals to 1 to n 1 plus x by k. Now after this we have 1 by gamma of x, and limit n goes to infinity x times e to the power, this is x gamma x. Sn minus ln is ln, where n goes to infinity is just gamma, and this can be taken inside the infinite product since this is the infinite sum, and infinite sum is power in power is just infinite product. So we have infinite product from k equals to 1 to n 1 plus x by k, and this will be e to the power minus x by k. So this k will just sum up and give Hn. And now this one is y stress representation for gamma function, just derived from Gauss one. Y stress representation. Now after this, to get the diagram of infinite sum formula, we just need to take log over the whole expression, and this gives us minus ln of gamma x. And one thing, since we just have n over here only, so we can just remove this part and directly put an infinity over here. That can be done. Yeah. So now this is the y stress representation. Now if we take log, we will have ln x plus gamma x, and the log of infinite product is sum of log of the terms, and so the sum from k equals to 1 to infinity, there will be ln of k plus x minus ln of k minus x by k. Now if we differentiate this, we get minus digamma of x equals to 1 by x plus Euler-Maclaurin constant plus sum from k equals to 1 to infinity, and then 1 by k plus x, that one is 0, and minus 1 by k. So if we bring negative to other side, we have diagamma of x equals to minus 1 by x minus Euler-Maclaurin constant plus summation from k equals to 1 to infinity 1 by k minus 1 by k plus x. Okay, so now if we bring this to other side, we have diagamma of x plus 1 by x equals to minus gamma Euler-Maclaurin constant plus sum from k equals to 1 to infinity 1 by k minus 1 by k plus x. Okay, so now this one is an interesting property. This one invokes an interesting property. So basically we have x times gamma of x equals to gamma of x plus 1. If we take log, we have log x plus log gamma x equals to log gamma x1. Now if we differentiate this, log gamma x just 1 by x, this is digamma of x, and this is digamma of x plus 1. So we see this is just digamma of x plus 1, which is negative of Euler-Maclaurin constant plus summation from k equals to 1 to infinity 1 by k minus 1 by k plus 1 x. Now this sum is an interesting one. Let us just observe like how it opens up. Diagamma of x plus 1 is just negative of Euler-Maclaurin constant plus, for this one we have 1 by 1 plus 1 by 2 plus 1 by 3 plus 1 by 4, and at some point we will raise 1 by k as well. I mean, is it necessary? 1 by x, let's say. So 1 by x, and then 1 by x plus 1, 1 by x plus 2, and goes on. Okay. In the next sum We'll begin with 1 by x plus 1, and then 1 by x plus 2, and then 1 by x plus 3, and goes in. So basically these terms cancels out. Every time after those should cancel out. So this just remains, which is just x, the harmonic number. It is just hx. So we have digamma of x plus 1 is equals to negative of Euler-Maslow constant plus x, the harmonic number. So basically, if we replace x by n, digamma of n plus 1 equals to negative of Euler-Maslow constant plus nth harmonic number. So here we have proved the most beautiful result in maths from scratch, from nothing to everything. So if I have to summarize this one, first of all we try to find an integral representation for gamma function. Yeah. And then after that we try to change that integral representation to product representation of Gauss. Yeah, product representation of Gauss, which was like this. And then to another representation of product where there was no infinite term, like this, to of where stress, and then to infinite series representation of digamma, and then finally we got the beautiful equation in maths. So this was a long journey, but I believe it was an interesting one and a fruitful one, and that you enjoyed. So if you did really enjoy, do like, share, subscribe. Thanks for watching. Look forward to seeing you in the next video.